Hello students and welcome to the continued lesson on complex numbers. We've talked about addition, subtraction, and multiplication. And before we move on to division, we have to talk about a new definition, which is called the complex conjugate. So given a complex number, a plus bi, okay, the complex conjugate, and sometimes we call it the conjugate just for short, but the complex conjugate is A minus BI. Minus BI. And that's all that it really means. It's just this, in a short way, it just means to multiply the imaginary part or the imaginary component by -1. Okay, so that's all it really means. And it's a definition, so we don't have to prove or explain a whole lot about or to justify this. But the reason we define this is that the complex conjugate is going to play a very important role in our work with complex and imaginary numbers. So let's look at a few examples here. So let's say I have a number 3 plus 4i, and I'll call this number z. Okay, let's say z equals 3 plus 4i. Okay. Well, the conjugate z bar, this is pronounced z bar, and this is just a notation for the conjugate of z. It's just equal to 3 minus 4i. Let's do one more. If I have a number, we'll call this k is equal to 2 minus 5i, then the conjugate k bar is really just equal to 2 plus 5i. So we just flip the sign of the imaginary part. And so if you're wondering why we do this, well, there's a really helpful property of the conjugate. So let's see what happens when we multiply two conjugates. So what happens when I do z times z bar using what I have up here? Well, z is 3 plus 4i, and z bar is 3 minus 4i. And so when we multiply this out, we will get 9 minus 12i plus 12i minus 16i squared. Well, looking at this example, we can see that the negative 12i and the positive 12i will cancel, and that will leave us with 9 minus 16i squared. But remember that I squared is equal to -1. Okay, let me write this a little neater here. I squared is equal to -1. So this is just 9 minus 16 times -1, which is just 25. Okay. So this is a little bit interesting here, that you have two complex numbers, multiply them together, they just happen to be complex conjugates, and when you're done, you get rid of the imaginary part altogether, and you end up with only the real part. Let's try the other one here. So let's try k times k bar. Well, we have 2 minus 5i times 2 plus 5i, and this leads us to get 4 minus 10i plus 10i minus 25i squared. And once again, these two middle terms cancel. We end up with 4 minus 25i squared. And again, I squared is -1, so that's just 4 plus 25, or 29. And so the main message that we can take away from all of this, and hopefully you can see this for yourself, is that whenever we multiply a number and its conjugate, we always end up with a real number. Okay, so I'll make a note here. So multiplying a complex number with its conjugate. So if we take a complex number and we multiply with its complex conjugate, we will always get a pure real number. That means we end up with a real number that has we end up with a number that has no imaginary components, and that is really nice when you are trying to get rid of imaginary numbers. If you don't like them, if in some cases where we can't really work with them or they complicate a problem, you can find a way to multiply them by their complex conjugates, and you always end up with a real number. Okay? And if you think back to your days in Algebra 1 or Algebra 2, this is similar to the difference of squares. Okay, it's similar to that, where if you have a plus b times a minus b, you're always going to end up with a squared minus b squared. So it's similar to that, but it's not quite the same thing. There's a thing where the middle terms cancel out. That's similar to this, but the more beautiful thing about multiplying complex numbers and its conjugates is that you always end up with a single real answer as the value. So now let's take a look at some examples of dividing by a complex number. So before we move on further and we go too far, let's review a little bit about what standard form means. Okay? So in mathematics, it's important that we all write our answer in the same format so that we don't have to keep doing conversions back and forth. So standard form basically means a few things. There's a few criteria. So there's no fractions in square roots. So a number like this (9 over 2), let me write this bigger. Okay. This is not standard. Okay. That's one of the rules. Other rules is no square roots or no radicals even in denominator. So even if I had the square root of 9 over the square root of 2, this is also not standard. And we also need everything to be simplest fractions, simplest radicals, and there's a few other rules. But the new rule here that I'm adding on is no complex, or I should say imaginary, numbers in denominator. And so we want everything to be written as a plus bi. That's what we're looking for, okay, when we're dealing with standard form of complex numbers. We don't want anything in the denominator. And so let's look at an example of that. Okay, so here I have an example of dividing complex numbers. I have 3 plus I divided by 2 minus 5i. Now, This is just a fraction of a complex number, but it is not in standard form. So what we're really trying to do is convert it to standard form, and we cannot have any imaginary numbers in the denominator. So the way that we're going to approach this is a little bit unusual, but we're going to multiply it by 1. Okay. So I know that this whole thing is really just equal to 3 plus I over 2 minus 5I times 1. Okay, I know this is a little bit weird, but if you think back to how do we deal with fractions, we often multiply by 1. Okay? And then after that, we convert 1 to the complex conjugate. And this is why complex conjugate are useful, of the denominator. So we take this 1, write that there. So we take this 1 and we change it into 2 plus 5I over 2 plus 5I. See there? So 2 plus 5I over 2 plus 5I, that's still 1. And we can choose to do whatever we want here, as long as we do the same at the top and the bottom. But we choose the complex conjugate of the denominator. And then we just multiply and we simplify from here. So all of that is equal to 3 plus I times 2 plus 5I divided by 2 minus 5I times 2 plus 5I. And we have a problem, we have two multiplication problems essentially. On the top we've got 6 plus 15I plus 2I plus 5I squared. On the bottom we've got 4 plus 10I minus 10I, and then minus 25I squared. And it's a little bit of work and it looks a little bit messy, but we can simplify this. On the top, that's just 6 plus 17I. And remember this part right here, since I squared equals -1, this is just equal to -5. Okay, so this is minus 5. On the bottom, middle terms will cancel, and you have 4. And again, this block right here, because I squared is equal to -1, this is just positive 25. So plus 25. Simplify this out. This comes out to, on the top 1, because we're taking the two real parts and adding them together, plus 17I, all of that over 29. Now we can go a step further, and we want this is one big fraction, but maybe we want to write it as a plus bi. So we can just split this fraction, 1 over 29 plus 17 over 29 times I. This quantity and our final answer are the equivalent, but this is standard form. Actually, they're both standard form, but this one is preferable. Okay, so there you have it, an example of how to divide complex numbers. Okay. All right, so here we have an equation, x squared plus 3x plus 11. We're asked to solve for x, and we want to give all solutions. And so all solutions here means that we want complex solutions as well. Okay, so not just the real answers now, all the complex solutions as well. So let's begin this, and this is a quadratic, and you can solve it any way that you'd like. I am going to just solve this by completing the square, because that's one of my favorite methods. And we have a 1 coefficient here, so that makes it extra nice. So I'm going to separate the constants from the variables, so I get -11 on the right side of the equation. So I'll make a note here when we complete the square, we need to separate variables and constants. Okay. And remember, we want to add something in here that will allow me to factor this thing perfectly. And that is 1/2 of the middle number squared. So this is going to be 3/2 quantity squared. And I have to do the exact same thing on the other side. Okay. That's 9/4 for those of you who are doing this mental math. So x, and then on the left side here, I'm sorry, this factors perfectly into x plus 3/2 quantity squared. Okay, so whatever we divide the middle term by, whatever the middle term is, you divide it by 2 to get this term, and you square it to get this term. And now on the right side of the equation, I get 11, so that negative 11, so that's negative 44 plus 9/4. So that gives me 45. I'm sorry, not 45, negative 35/4. So on the right side of the equation, this leaves me with negative 35/4. And then we can take the square root of both sides. Okay. Now, if you recall, back in Algebra 1 and maybe Algebra 2, at this point you would stop and you would say non-real answer. Well, that's true, it is a non-real answer, but now we're going to take this a step further and just find out what the non-real answer is. So on the left side it becomes x plus 3/2, and on the right side we have plus or minus the square root of negative 35, okay, over the square root of 4. And this is really just plus or minus. I'm going to split the negative 35 into negative 1 and positive 35. And my denominator here, of course, gives me 2. And then we've got, I'm going to leave the left side alone for a bit and just work on a little bit more on the right side. But we keep in mind that the square root of negative 1 is really equal to I. So this is plus or minus I times the square root of 35 over 2. And then subtract negative 3/2 from both sides. So we get x equals negative 3/2 plus or minus. I'm going to just move this I here to the end. So square root of 35 over 2 times I. And that's my final answer. And this is a bit of an unusual equation and an unusual problem altogether, especially if you haven't seen complex numbers before. And it says that there are no real solutions to this. And by real, we mean x-intercept. So let me graph this too so that you can see. Okay, so I've typed this in here, this equation into my calculator here, and I hit graph. I'm going to use the standard window. And you can see it's barely visible up at the top there, so let me change my window. I'm going to increase the Y max to like 30, just so you can see a picture of it a little bit better. Now, looking at this here, this equation has no x-intercept. You see the x-axis here, so it doesn't have any x-intercepts, and yet it still has a solution to the problem. And that's because the solution is imaginary. So it means this shows that it doesn't really have a physical representation on the graph, but there is a solution. Okay, and there you have it, a lesson on complex numbers and a scenario with solving quadratics where the solution itself is a complex number. And to give a little bit of perspective on this, imaginary numbers, I think it's just a very unfortunate name. People just say, oh, well, it's imaginary. Why do we have to deal with it? Well, it comes about because mathematicians were solving problems and they ended up with situations like this where they didn't have a solution for. So they invented a new variable called I that represents this, a new number, we named it I, that represents the square root of negative 1. And then you may ask, well, why do we bother with all of this? Well, there was a time when the number zero didn't exist, and you can imagine like people doing problems, and they're having these issues like, what's 5 minus 5? Well, we don't know what that is, so they probably just wrote no solution until somebody came along and invented the number zero. So the imaginary number, occupies that same space where it's definitely a new concept, but it was necessary in order to complete some of the more difficult and some of the higher level math problems. Okay, so a brief introduction into the world of complex numbers.